this video, we'll be studying about the combination of capacitors. Capacitors, right? See, you already know that in I think thermodynamics, you have already studied about the combination of this rods. They form like resistance. Okay, here there will be two combinations. The one is series, the other one is parallel. Right? In series combination, the first case will take series combination. Okay. In series combination, let's say this is our combination, right? Capacitors are connected, applying voltage V. Okay. Now we need to let's say capacitance is C1, C2. Now we need to find equivalent capacitance for this circuit, right? So assume, let's say the potential across this is V1, across this is V2, across this is V3, right? So when the charge moves from here to here, let's say this capacitor C1, it gets a positive charge Q, okay, right? And this will be on this phase, right? Plus charge. Then this will get negative charge Q. Then since they are in series, this will also get what? Same charge. Means this will also get positive charge Q, this will get negative charge, this will get positive charge Q, this will get negative charge, right? So if you see that potential across V1 is equal to, it will be what? It will be the charge on that capacitor on the capacitance of C1, that is actually your C1, okay. Similarly, V2 will be Q2 by C2 and V3 will be Q3 by C3, right? Now you know that your net potential P potential, it will be the summation of potentials, right? So you will get V is equals to, sorry, I think I have written a, this will be Q, okay? Q by C1, Q by C2, Q by C3, okay? So net potential will be, you take Q as common, 1 by C1 plus 1 by C2 plus 1 by C3, right? And if you draw this circuit in reduced form, something like this, okay, right? This capacitor having capacitance C equivalent, which is the equivalent capacitance for this whole circuit, okay, and this applied potential is V. So you can see that V will be Q upon C equivalent. This charge will be what? It will be same, okay. So from here, this equation you can write, substitute V as Q upon C equivalent, okay, equal to Q 1 by C1 plus 1 by C2 plus 1 by C3. Q gets cancelled out, you will get 1 upon C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C. This will be your equivalent capacitance across a series of capacitors, okay. Now we'll see which is this result. If you compare with the resistance one, this result is opposite. In parallel, we used to get 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Okay? In this, when capacitors are connected, you will get this answer, this result. Okay? Now, we'll see characteristics, okay, of series combination. Right? The first characteristic is that all capacitors will have equal charge. Right? The second one, the potential difference is inverse proportional to capacitance. Right? The third, These combination are used when high voltage is divided among several small voltage, right? Suppose that this is a high voltage and we need to divide it in small voltages, right? Then series combination is used. Okay, we'll add some capacitors and voltage will be divided into small one. Okay, so these were the three characteristic about the series combinations. Okay, now the second one, that is your parallel combination, right? In parallel combination, your capacitors will be connected somewhat like this, right? Suppose we are supplying the charge Q. Okay, this capacitor C11, C2, this is C3, right? Let's say this gets a charge Q1, this gets a charge Q2, and this gets a charge Q3. Okay, now we need to calculate equivalent potential. Okay, if you see that potential across the C1, the C2, the C3, they will be what? It will be same as the supplied potential. If we consider supplied potential as okay. Now, what will be Q1? Q1 will be C1 into V. You know that potential across this will be V, and across this will also be, across this also will be V, because they are all connected in parallel, right? Q1 will be C1 into V, Q2 will be C2 into V, right? And Q3 will be C3 into V, right? And our net charge will be, which has been given to these capacitors. It will be Q is equals to Q1 plus Q2 plus Q3. So Q is equals to C1V plus C2V plus C3V, and Q can be written as C equivalent into V. So it will be C1 plus C2 plus C3 multiplied by V. If we take common, V as common, V will be cancelled out and you will get C equivalent is equal to C1 plus C2 plus C3, which is opposite to the when we what we get from resistance. In resistance, we get 1 by C1 plus 1 by C2 plus 1 by C3 equal to 1 by C equivalent. But in case of capacitance, when they are connected in parallel, we will get this, right? So write some characteristics. Characteristics already, I think you can also tell by looking the that all capacitor will have same potential difference, right? And in the case of series, they all are having same charge, right? Here, charge is varying in proportion to capacitance, right? And parallel combination are used when uh, we require a large capacitance so that charge can be accommodated. Why? Uh, in case of large requirement of capacitance, right? When we require a large amount of capacitance. So this was uh, characteristics of parallel combination. Okay. In the upcoming videos, we'll be doing problems related to combination of capacitors.